And before I get into the material, I want to address a couple of things about the course itself. So first of all, I hope everyone is doing well in light of the sort of ridiculous situation we've been placed into. Hope everyone is safe and healthy and all that. And if there's anything that I can do to help make this transition easier for you, please don't hesitate to let me know. We're trying to be as flexible as possible. So obviously our course kind of got turned upside down. We had to make a lot of changes on the fly, and anything that we can do to make this better, we certainly appreciate hearing about it from you. One thing that I do want to address that I've heard a few comments about recently is sort of the perception that how we're doing the exams with a webcam system is not fair to all the students. There's concerns that some students don't have a webcam and they can still take the exam. There's going to be a lot of cheating. So I want to address a few topics related to that. The first is that, I guess as a bit of a cop-out, it wasn't my decision to use the webcam system. These types of decisions are made at sort of a departmental level. I certainly weigh in on those, but it's not exclusively my decision to do that. But more importantly than that, I think the important thing to realize with this whole semester is that, there's no nice way to put it. Everything just sucks. Like any decision that we make to try to deal with what we've been, what's been thrown at us is just not going to be perfect. There's no perfect solution for any of this. So we wanted to use the webcam system to sort of, have some level of security in our exams that we no longer are able to do without CASA being in operation. But at the same time, since this was a very sudden change in the course, most webcams are now back ordered because everyone around the world is converting to remote learning and remote teaching and remote working, whatever. So webcams are just being bought up like crazy. The city's in a lockdown, so expecting you to go shopping for a webcam is not really reasonable. So we want to make sure that everybody can take the exam, even if you don't have a webcam. So, this is going to rely on a bit of trust from us, and that all of you sort of have to partake in that trust. There is, of course, the possibility with or without webcams that this new online format is going to make it a lot more difficult to catch people who are cheating. I'm certainly aware of that, and I know that some people in this class will cheat, and they won't have any qualms about that. But what I would say is, for the people that decide to be honest and not cheat, so who work hard at learning the material, take the exams, get the grades that you get, first of all, you have my respect, whether that means anything or not. But second of all, the point of college is to set yourself up for a successful career and a successful life. And if you have the work ethic and the honesty and the integrity to go through this course and do the best that you can the rest of the way and not to, cheat and cut corners, you are doing a lot more to set yourself up for success in the future than the students who are going to just take this as an opportunity to cheat. Okay, so those students, they might help their grade this semester. They might get a higher grade than they would have otherwise, but somewhere down the road, this is going to catch up with them. Their lack of knowledge that they gained in this course, they're not going to learn anything. The obvious lack of integrity that they have to be willing to cheat, all of that's going to catch up with them in the future. So I assume right now in the live session, I'm preaching mostly to the choir, because I think the people that are taking the time to join me live are likely the people that have all intentions of putting in a lot of effort to the course. And so if that's true about you, and if that's what you're going to do, then I tip my hat to you, and we're going to try to make this semester the best that we can in terms of learning chemistry and fairly evaluating the students. So that's my little pitch about that stuff. So what I'm going to do now to get into the exam review session is I'm going to share my screen with you. So what you should see my tablet screen popping up on your screen in a moment here, once I pick the right one. Sorry, I don't think I did that right. All right, so you should see my desktop, which has the periodic table on it now. And then if I go into the PDF, hopefully that's showing up for anybody. If anybody is having trouble seeing that, let me know now. All right, I'll assume the silence is an indication to continue. All right, so getting into the exam material, the first thing I want to start with is a brief review of things that I didn't really cover well in class, but there are a couple exam questions that are on there. It's a small part of the test bank, so chances are you won't get asked about this. But one thing I want to talk about a little bit is the shape of the hybrid orbitals. I think my pointer is gone, so let me get that back. Okay, good. All right, so we want to talk a little bit about the shape of hybrid orbitals. So one of the major topics in chapter 4, the first part of the review that we'll cover today, is hybridization, and the idea that the central atom atomic orbitals can mix together, can hybridize to form mixed orbitals sp, sp2, sp3 as we denote them. Most of the questions on hybridization are going to just ask you to predict the hybridization, and we're going to have at least one question in the review along those lines. But there are a couple things in there about the shapes of hybrid orbitals, and it's really not terribly difficult to keep straight. So if you have an individual hybrid orbital, one sp orbital, one sp2 orbital, one sp3 orbital, they all have qualitatively the same shape. So they're going to have, they're a mix of s and p, so they're going to have sort of a large lobe from the p part, which I already messed up the drawing. I'm at a different angle than I normally am, so my artistic skills are going to be eroded even further. And then they're going to have a smaller lobe. So basically, every hybrid orbital has sort of this basic shape. It's going to be two lobes, and they're going to be unequal size. Now, there are subtle differences between sp, sp2, and sp3. Basically, the relative sizes of these two lobes they're going to be more equal if it's sp and less equal if it's sp3, but we're not going to ask for those sort of subtleties. As long as you know that the shape of an individual hybrid orbital has two lobes and those lobes are unequal size, that's sort of the depth that we need you to know this. Now, the other thing that we could ask you about as well is the shape that the whole orbital set makes. So when you have sp hybridization, you have two sp orbitals. When you have sp2 hybridization, there's three of them. And how do they arrange themselves? Now remember that they arrange themselves according to the shapes of the molecules that they exist in. So if you have sp hybridization, you're going to have two orbitals that are 180 degrees apart to be able to form a linear molecule, because linear molecules are what is associated with sp hybridization. If you have sp2 hybridization, you're going to have three of those orbitals, and they're going to arrange themselves in a trigonal plane, as this picture in yellow shows, where the three orbitals are going to have 120 degree angles between them, and they're going to be able to then form trigonal planar type molecules. And then finally, sp3, the only other one that we would ask you about potentially in this exam, a little bit harder to draw because it's now in 3 dimensions, but this is going to be a set of sp3 orbitals where there's now 4 of them, and they're going to be arranged in a tetrahedral arrangement with 109.5 degree bond angle. So each set of hybrid orbitals, sp, sp2, sp3, they're going to arrange themselves in a way to basically form the shapes that are associated with them, either linear, trigonal planar, tetrahedral. All right, so I wanted to just quickly cover that. So I will pause now. Is there a question coming in? Is that a message of some sort? All right, so let me see if I can, I'll figure this out. All right, so we have one message from the crowd. Is there a recording on here or on YouTube? So someone said we can see it. Thank you, KC. And someone asked, is there a recording? That was Caitlin Cortez. And then Mohammed asked, is there a recording on here or YouTube? Yes, this is currently being recorded for YouTube, and I'll have it up later this afternoon after we finish. So if there's any questions about this topic that I just covered, please weigh in now with, either.
I have a question.
Yes, please go ahead.
Okay, can you repeat the one of the sp3? I didn't quite get that. Can you go over that one real quick?
Yeah, and then we had another question texted in, so I'll get to that in a second from Marina. Okay, so sp3, your question was about that. So the shape of an individual sp3 orbital, so this would be the shape of an individual orbital, is roughly going to look like this. And then in the set of sp3 orbitals that are all together in a molecule, shown down here, one of the lobes is sort of obscured from view, but you're seeing the larger lobe sort of protruding. And sp3, remember, is associated with a tetrahedral electron group arrangement. So this gets messed up. But anyway, this is associated with tetrahedral. And so that's going to be the shape that the three sp3 orbitals make up when they form that sort of arrangement. So it's going to be 4 orbitals, 109.5 degree bond angles, as is normally the case for tetrahedral arrangement. Okay, and then the other question was, is sp linear? Yes, that is also correct. So sp's hybridization is associated with the linear geometry. So each hybridization is associated with a certain geometry, and this one would be trigonal planar. My pen is lagging, which is a little bit scary now. So hopefully I can write okay. So this is going to be trigonal planar. So each of these hybridizations is associated with a specific electron group arrangement, and then that's going to be the shape that the hybrid orbitals make up in those particular molecules. All right, any other questions on this topic before I move on? lagging a little bit here. Hopefully it comes back. And then the other one is, so the hybrid orbital shape you drew is sp3 because they're not even. The hybrid orbital shape I drew is basically for any of them. Whether it's sp, sp2, or sp3, they all have basically the same shape. As I said, there's some slight differences between them, but they're going to be roughly the same in terms of the shape of an individual orbital. What is different is shown at the bottom here is how they arrange themselves in a molecule when you have a whole set of those orbitals. Okay. All right, so I think we're all set on that topic. So let's go ahead and move on to the rest of the review. My tablet is having trouble with all these different things going on at once, so hopefully we can get through this okay. All right, so then moving on to the first question on the review. So there are 20 questions as they're going to be on the exam, and the arrangement of topics is basically identical to the exam. So you'll see that we're going to have just about 5, I think, questions on the first material, chapter 4, and then we'll have a few more questions on chapters 5 and 6 than that. So the exam is a little bit more heavily weighted till chapters 5 and 6, but it's not going to be, it's going to be relatively equal for all 3. All right, so if you'll recall, the topics we covered in chapter 4 were molecular shape and also bonding in covalent molecules. Feels like it was a different lifetime when we covered that stuff, but we're going to come back to it on this exam. Okay, so the first question deals with the shapes of molecules. We want to know the electron group arrangement and molecular geometry for the anion SeF3-. So in this material here in chapter 4, the first thing you have to be able to do is draw a good Lewis structure. That's still going to be something we have to do. We learned that in chapter 3, but for a lot of this stuff dealing with shapes and orbitals, you have to be able to draw a Lewis structure. So the first thing we're going to do is we're going to count the electrons and draw a Lewis structure. Oh man. All right, so selenium, and then we have fluorine in this anion, and we have a negative charge. So those are going to be the 3 things that we're going to contribute to the number of electrons that we have. And so what we're going to do is we're going to go to the periodic table. And then we're going to look at how many electrons each of those have. So selenium here, Se, is in group 6. So that's going to contribute 6 valence electrons. Each fluorine from group 7 is going to contribute 7. And so then when we count electrons, we'll go back to that. And we have 1 selenium, which is going to contribute 6 electrons. We have 3 fluorines in this anion that are going to contribute 7 each. And then we have a negative charge, which adds 1 more electron to the total. So in total, we're going to have 28 valence electrons in this anion here. So when we draw the Lewis structure, we need to make sure that we use 28 valence electrons. I'm not going to go through the Lewis structure too slowly because we've already covered this topic a while ago, but as a review, we start with single bonds to all the outer atoms. So we're going to put our 3 fluorines in. The whole thing has a negative charge, which I'll indicate as well. And then what we want to do is complete the octets of the outer atoms first. So we're going to put 6 additional electrons onto each fluorine to give them a total of 8, 2 from the bond and 6 from the lone pairs. All right, so we've completed the octet of the outer atoms, and we take stock now of how many electrons we have left. So that's 3 octets for a total of 24, which means we have 4 more left, all going on the central atom. So we're going to put 2 more pairs, or 4 total, on the central atom as lone pairs. Now for VSEPR, which we're doing here to determine the molecular geometry, we don't really even need to worry about if there's any double bonds or not. Those are going to sort of, that doesn't really affect the shape at all. But what we can do then is, I don't know why my microphone's really hot right now. We have a question come in. I don't know what that was. Okay. And then we have, so this is the Lewis structure, and we can figure out then the AXE arrangement. So it's going to be our central atom. We have 3 atoms bonded to us. It's going to be AX3. And then we have 2 lone pairs on the central atom to make it AX3E2. All right, so that's going to be our sort of AXE notation if you like to go that way. And so then from there, what we need to think about is what is the electron group arrangement and the molecular geometry. So the first thing for electron group arrangement is going to come from the number of electron groups that we have. So we have 3 X's and 2 E's, which means the total number of electron groups, or what is often called the steric number, is going to be 5. And anytime you have 5 electron groups, whatever the combination of atoms and lone pairs is, that's going to give you an electron group arrangement that's trigonal bipyramidal. God, my pen is lagging badly right now. And so the electron group arrangement is going to be trigonal bipyramidal. All right, so that's going to be the first part of the answer is trigonal bipyramidal electron group arrangement. And so if we draw that out, what we end up with is five electron groups that are going to be in a trigonal bipyramidal arrangement with selenium at the center. And remember, whenever we have 5 electron groups, if we have lone pairs, they always go on the triangular part of the electron group arrangement. So we're going to put 2 lone pairs on the triangle, like that, and then we're going to have fluorines on the other 3 positions. All right, so that's going to be our molecular shape, which has the 2 lone pairs on the triangle and the 3 fluorines there. And then what we call this, as you recall, it's sort of sideways now, but this is going to be what we refer to as T-shaped. All right, so there is a table that I put in the notes that sort of summarizes all the different geometries. I do think drawing them out is helpful, so you don't have to necessarily just memorize all of them, but at any rate, what you need to know is that AX3E2 corresponds to the T-shaped geometry. So the correct answer then would be C, which has trigonal bipyramidal for the electron group arrangement, and then T-shaped for the molecular geometry. So 2 different parameters that we use to classify the shapes of molecules using VSEPR. All right, so do we have any questions then on the what I just covered? I don't really want to record the meeting. Let me turn the camera off. All right, any questions on this? How do you find the steric number? So steric number is just total number of electron groups. So if we go back to that problem, what we saw here was that we had 3 X's and 2 E's. So the sum of those two, 3 plus 2, is what we call the steric number. And that's always going to define the electron group arrangement. So anytime you have 5 electron groups, whether it's AX5, AX4E, AX3E2, AX2E3, any combination that adds up to 5 would be a steric number of 5 and then give you a trigonal bipyramidal electron group arrangement. So that's how we find that. And so whenever you ask for electron group arrangement, all that really matters is the total number of electron groups around the central atom, not so much whether they're bonded atoms or lone pairs. Okay, do we have any other questions on this? All right, so let's move on to the next one, which deals with polarity. So once we can figure out the molecular shape, the other thing that we can determine from that is whether the molecule is polar or not. So, sorry, my tablet is lagging, so I'm having trouble getting this. Okay, so which of the following molecules have a non-zero dipole moment? That's what this question asks. So we're given 5 here. Now, in reality, there's not really much of a shortcut to this. We have to basically sketch out the Lewis structures and figure out which one is which. Now, when we have the term here in the question, non-zero dipole moment, that's sort of a fancy way of saying, is it polar or not? So we want to. So if you see, 0 dipole moment means nonpolar, non-zero means polar. And really, on this test, all we have to be able to do is distinguish polar from nonpolar. We're not going to worry too much about ranking molecules in terms of their polarity. So if you get a question that asks which of the following is the most polar, basically that would mean that one of the molecules is polar and the rest aren't. All we have to be able to distinguish is polar from nonpolar. Okay, so if we go through these sort of molecules that we have here, we have to draw out the structures. And I'm not going to do that in a lot of detail, but what we would get for NF3, all right, so it seems like my tablet is working better now that I shut my camera off. So you won't be able to see my face that's made for a radio, but you'll be able to hear me hopefully and still see the screen that I'm sharing. All right, so for NF3, what we get is this sort of arrangement. It's a trigonal pyramidal molecule, AX3E, if we're using that notation. And it's helpful to know some shortcuts about this. So in molecules that have just one type of outer atom, all of these are fluorides. So fluorine would be the outer atom in all of these. So in that case, if you have one lone pair, or any case with one lone pair, that will be polar, okay? So the first one, NF3, is definitely polar, has one lone pair. If we go to BF3, what we get is a trigonal planar molecule. And so this is going to be AX3, and any of the geometries that have 0 lone pairs we know are going to be nonpolar, okay? So that's going to be nonpolar. Anything with 0 lone pairs is, again, essentially when the outer atoms are all the same. Xenon difluoride, XEF2, is sort of a weird one. It's a fluoride of xenon. And what we would get for this one is it's total of 5 electron groups, but only 2 of them, the 2 fluorines, are atoms. And so we have xenon at the center. All the lone pairs go on the triangle, as we said, and then you would get the 2 fluorines top and bottom. This is a linear molecule, AX2E3. And so anything that's linear and also has 2 identical outer atoms is going to be nonpolar as well, okay? So for the molecules that have just 3 total atoms, this is the only one in this set that has 3 total atoms. Remember, when you have 3 atoms in the formula, the only options are linear and bent. Linear molecules are nonpolar, bent molecules are polar. Linear molecules being nonpolar specifically when both outer atoms are the same, but that's sort of a key distinction between the linear and bent molecules that you can have. And then if we go to the last 2 answer choices, another fluoride of xenon, tetrafluoride in this case, this one has 6 total electron groups when we draw it out, so they're going to go octahedral, and then you're going to put the 2 lone pairs that you have top and bottom, and you're going to have the fluorines in a square plane. All right, so this is maybe not the most intuitive one, but because the 4 fluorines are all arranged in a square, you have 2 pairs that are 180 degrees apart, the dipoles cancel out, and so any square planar molecule would end up being nonpolar. All right, and so again, in this section where we talk about polarity of molecules, there is going to be a table in the notes if you go back to that section that sort of summarizes all of that. But again, I wouldn't recommend memorizing the table. I would recommend sort of trying to understand how the molecular shape relates to polarity. And in most cases, like I said, it's fairly straightforward. And then finally, the last one, SF4, what we get is 5 total electron groups. So one of those is going to be a lone pair, and then the other 4 are the fluorines. This is called the seesaw geometry, one of the ones that's a little bit most difficult to visualize, but the AXE notation is AX4E. I forgot to write it up here, AX4E2 for xenon tetrafluoride. This one's AX4E, and as we said earlier, anything with 1 lone pair will definitely be polar. So in problems like this, there's a few helpful things to look for. You would have anything with 0 lone pairs is typically going to be nonpolar. Anything with 1 lone pair will be polar. And then you have more than 1 lone pair, there's a couple possibilities depending on what the shape is. But here we're asking for the polar molecules. That's going to be NF3 and SF4. So the correct answer for this would be also C, number 1, I think I screwed that up. Should be 1 and 5. Yes, C. All right. So questions on this one? All right, I silenced, and I don't think there's any new messages to come in. All right, so you can always stop me later on, but I think I'm going to go back to the PDF, sorry, this one, and move on to the next question so we can not be here too long today. All right, so then going back to, so number 3 now deals with hybridization. We talked a little bit about hybridization at the beginning, just sort of reviewing the shapes of the orbitals. Most of the questions on hybridization are going to involve you basically determining what the hybridization is, as this problem asks for here. So what is the hybridization of the central atom in SeF3 minus? So we drew the Lewis structure of this earlier, so we already know that this anion is going to be AX3E2. and the steric number was 5. Okay, so we determined that in the first problem when we were discussing its molecular geometry and electron group arrangement. And this you also need to know when you're determining the hybridization. So the steric number, the total number of electron groups, here being 3 plus 2 is 5, that's going to determine what the hybridization is. And so the way we figured that out then is our central atom, selenium, it's beyond atomic number 10, so it can go beyond an octet. It can have more than 4 orbitals hybridized. So the orbitals that are available for hybridization are an s orbital, 3 p orbitals, and then up to 2 d orbitals. There's a total of 5 d orbitals, but only 2 of them would ever be used for hybridization. And because we have a steric number of 5, we need to have 5 orbitals hybridized. So we're going to box out the first 5 of those, and that's going to tell us that the hybridization is going to be sp3d. Okay? So for any time you have 5 electron groups, you're going to have sp3d hybridization. So I guess I like the letter C in this test because that's also the answer here. So as a reminder then, the number of electron groups that a molecule has, or an ion, is going to determine what the hybridization is. Okay? So if we have possibility of going with 2 through 6 electron groups. Those are really the only possibilities we'll consider. And these are all going to give you a different hybridization. So 2 electron groups, we hybridize 2 orbitals, which is sp. 3 electron groups, we hybridize 3 orbitals to make it 2. And then 4 electron groups, we hybridize 4 orbitals, making it sp3. 5 electron groups, as we just saw, is sp3d. And then 6 electron groups is sp3d2. All right, so again, for these problems, you have to be able to draw a good Lewis structure, which we did in the first problem for this one, so we didn't do it again. But once you have the Lewis structure, it's not so important whether the atoms are singly or doubly or triply bonded, but the number of total electron groups, the number of atoms bonded to the central atom, and the number of lone pairs is going to be critical for determining hybridization. All right, so any questions on this problem here? All right, I think I get a notification when there's a text message, so I don't think there's anything coming up, but let me just double check. I'm still getting used to this whole system, so. All right, so sorry, we had some questions come in that I missed. Okay, so going back to, so someone sent what looks to be a video of someone crying. So, well, I guess you can all see that, but I won't address that one for now, but hopefully everyone's doing all right. So the first question that I missed was, shouldn't the lone pair be on the top or bottom for SF4? So when we go back to SF4, what we have to recall for SF4, going back up to here, is that this has 5 total electron groups that are going to be in a trigonal bipyramidal arrangement. And anytime we have the trigonal bipyramidal arrangement, no matter how many electron pairs you have, lone pairs you have, they're going to always go on the triangular part. So I didn't draw it the same way, but basically this part here is the triangle in the trigonal bipyramid. And in the trigonal bipyramidal electron group arrangement, however many lone pairs you have, 1, 2, or 3, will always go on the triangular part. It's not super intuitive why that is, but those lone pairs want to get as far away from each other as possible, which is why they're going to arrange themselves in that way. Now, if we go back to address the other questions, which I think were on this here, so we would never go up to F, so I'm assuming that refers to hybridization. Yes, so hybridization, the maximum number of electron groups, as we said, is 6, which means you can go sp3d2 is the sort of maximum that you go to. So you can hybridize s orbital, 3p orbitals, up to 2d orbitals, but never anything involving f orbitals. And then the question that came in most recently was, for the whole chapter 4, will we have to draw a Lewis structure for each question? Probably the first 3 questions on the exam will involve a Lewis structure, as we just talked about in the review. The last part of chapter 4, which is going to be our next 2 questions we go over, is molecular orbital theory. And for that, you typically want to avoid the Lewis structure, because molecular orbital theory sort of gives you some information that the Lewis structure won't. All right, so I have a notification of something. So, all right, so I think we're all caught up with messages on this. So let's go back then to the, let's go back to the review session. And we're back. Okay, now we're back. All right, on to number 4, again, dealing with the last 2 topics of chapter 4, which are molecular orbital theory. So in this question, it's more of a sort of conceptual or general question about MO theory, which typically on the exam you will have one like this. So the way it's going to be organized is one of the questions on molecular orbital theory will be either a conceptual question or a relatively simple one about MO theory, with just s orbitals, and then the other question, as we'll get to in a little bit, is going to deal with the p block elements, the molecular orbitals for those. All right, so in this question, we want to know which of the following will increase the bond order in a diatomic molecule. So what we'll recall from molecular orbital theory is that bond order is given as 1/2 times the number of bonding electrons. So when we have molecular orbital theory, a molecular orbital diagram, you're going to have some electrons that are in bonding orbitals and possibly some electrons that are in anti-bonding orbitals. And the difference between these, or half the difference between these, is going to tell you what the bond order is, okay? So with that mathematical relationship in mind, if we want to increase the bond order, there's two ways that we can do that. So if we make this term larger, the number of bonding electrons larger, that will increase the bond order. So if we add electrons to bonding orbitals, that's going to make the bond order go up. And then the other way that we can make the bond order larger, so that would increase the first term. If we want to also then decrease the second term here, that would make it larger mathematically. So if we decrease the number of electrons in anti-bonding orbitals, that will also make the bond order go up. So there's two ways of increasing the bond order. If we remove electrons from an anti-bonding orbital, that would then make the bond order also increase. So if we're forming ions, let's say we start with a neutral molecule and then we form an ion, if we add an extra electron and it goes into a bonding orbital, that will increase the bond order. If we remove an electron to make a cation and that comes out from an anti-bonding orbital, that will also make the bond order larger. I wrote that wrong, sorry. So both of these will make the bond order larger, so the correct answer is choice E. Adding electrons to a bonding orbital will make it larger, and then removing electrons from an anti-bonding orbital. The opposite to adding electrons to an anti-bonding orbital would make it smaller, so that's not correct. And then removing electrons from a bonding orbital would also make it smaller. So the two that make it larger are A and D, and then the correct answer then would be E, that two of these choices will increase the bond order. All right, do we have any questions on that problem or that topic? I don't know why I'm not in the meeting anymore, but all right, so I don't see any new messages coming in or anyone shouting out questions. I don't think. So let's go on then to the next one. All right, the next one is our other molecular orbital problem. And this kind of covers all the things that we would typically ask you in a question like this. So we're going to give you a molecule or an ion, diatomic only for molecular orbital theory, and we're going to ask you some combination of the following. What is the bond order? What is the number of unpaired electrons? Those are the two main questions that we will ask. So for this problem here, you have to draw out the orbital diagram and go through and figure out what the answer to these two questions are. So what we have to remember then for these is the ordering of the molecular orbitals. So in oxygen, we have 2 s valence orbitals, and we also have 2 p valence orbitals, 3 of them. And when these guys mix together to make molecular orbitals, what you're going to get from the 2s orbitals are a sigma bonding and a sigma antibonding orbital. And then what you're going to get from the p orbitals are going to be sigma and pi. In oxygen, the sigma comes first, and then pi. So you're going to have bonding at the bottom. Remember, the bonding orbitals are at lower energy than the antibonding orbitals. And then at higher energy than the atomic orbitals, you're going to get the pi and then the sigma. And it's going to be pi star, meaning that it's antibonding, and this one up here is going to be sigma star. All right, so we have anytime orbitals mix together, we get bonding and anti-bonding. Bonding orbitals being lower than the atomic orbitals, anti-bonding orbitals being higher. Now, for molecular orbital problems, the important thing is to know the order of these molecular orbitals that are in the center of the diagram. So sigma 2s, then sigma star 2s. For oxygen, it's going to be sigma 2p, then pi 2p, and then pi star and sigma star at the top. Recall that for the first half of the p block, if you're dealing with boron, carbon, or nitrogen, these two switch. But for oxygen, this is the correct order. And then the next thing you're going to have to do is put them into, put in the correct number of electrons. So here we have O2 with a positive charge, O2 plus. And so to count the valence electrons in O2 plus, we're going to have 2 oxygens, which each has 6 valence electrons. We're going to remove one for the positive charge because it's a cation. And so we're going to have a total of 11 valence electrons. And so then what we're going to do is we're going to populate these molecular orbitals with our 11 valence electrons going from the lowest energy orbital at the bottom up to the highest energy orbital until we run out of electrons. We're going to put 2 electrons per orbital, and we're going to follow the same rules that we used for atomic orbitals earlier in the course, okay? So 11 electrons, we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then our last one goes up here in this pi star 2p. So then the 2 questions that this asks are going to be bond order and number of unpaired electrons. So the bond order we're going to have, again, is 1/2. The first term in the bond order calculation is going to be how many bonding electrons we have. So bonding electrons are going to be ones that are in orbitals that don't have a star next to them. So they're going to be these 2 that are in a bonding orbital, 4, 6, 8. So no more than 8 of our electrons can be in bonding orbitals, and that's what we have here, 2, 4, 6, 8. The rest of our 11 electrons should be anti-bonding. We see that there's these 2 here that are in sigma star 2s. The last one that we put into pi star. So 3 of our electrons are going to be anti-bonding. So it's going to be 1/2 times 8 minus 3, or a bond order of 2.5. All right. And then finally, the number of unpaired electrons. We just have to look at the diagram and figure out how many spin-up electrons do not have a spin-down electron in the same orbital. And what we see is that only this last electron here is unpaired. These 2 are paired, these 2 are paired, these 2 are paired, these 2 and these 2. The last electron we put in up here is unpaired, and so that's going to be the only unpaired electron we have. So a bond order of 2.5, and the number of unpaired electrons is 1. Now there are some helpful things to remember about molecular orbital theory that are going to at least help you make sure that your answers are reasonable, in some cases provide you a shortcut for these. So the first thing is that in these types of problems, the molecule or the ion that you're considering is either going to have an even or an odd number of electrons. And if it has an odd number of electrons, that's going to mean 2 things. First of all, it means you're going to get a fractional bond order. So if you have an odd number of electrons, your bond order is going to be something 0.5. So if you don't get that for an odd number species, then you must have calculated it wrong. And similarly, what's even easier about odd number species is that odd number molecules or ions, the number of unpaired electrons will always be 1. If there's an odd number, that's the only way it can arrange itself. You can never have anything other than that. Now, if the molecule or the ion has an even number of electrons, then the bond order will be a whole number, but the number of unpaired electrons could be 0 or 2. So you really have to draw out the diagram correctly to figure out how many unpaired electrons you have. But there's not going to be too many variations on these types of problems. We're going to give you some molecule or ion, and we're going to likely ask you something related to the bond order or number of unpaired electrons. There's not really much else to that we expect you to know. So do we have any questions on molecular orbital theory or this problem in particular? So the question is, how would there be 2 unpaired electrons? So if we went so let's say we had instead O2 by itself, neutral. So there would be 2 unpaired electrons if you have the last 2 electrons going into a pi or pi star orbital. So if we had O2 without the positive charge, we would put one more electron here, and those 2 would end up unpaired. So there can be 2 unpaired electrons because remember, by Hund's rule, if we have 2 orbitals at the same energy, which is what we have for the pi and the pi star, we're going to fill those with 1 electron each before we pair them up. So in a case where you have pi orbitals or pi star orbitals, each one gets 1 electron first before you add the other ones in the same orbital. So in that case, you can have 2 unpaired electrons, O2 being the most common example of something that would have 2 unpaired electrons, but there are many others that could as well. Okay, and then any other questions on this? All right, so thanks for that question. Let's move on then to the next topic. So we are going to move now into Chapter 5 material if you're trying to keep track of where we are. So Chapter 4 is, as we said, the sort of smallest part of this exam. There's going to be 5 questions on Chapter 4, the rest dealing with the more recent stuff, Chapters 5 and 6. So the first major topic in Chapter 5 is going to be atomic mass. And so here we have a hypothetical element TT, which just by coincidence has my initials, and it has an atomic mass of 132.2145. If it has 2 stable isotopes, with 131 having the mass of 130.9856, and then the 134 isotope has a mass of 133.9767, what is the percent abundance of this second isotope, 134 TT? Okay, enter your answer with 2 decimal places. So this is sort of the typical type of problem you'll have on here, and what we have to recall for the definition of atomic mass is that there's really one equation that governs this. So in a problem that deals with atomic masses and isotope masses, we would automatically want to think of this equation here. The atomic mass is the weighted average of all of the isotope masses. So it's going to be the abundance of the first isotope, which I'll call A, times its mass, where the abundance is the percent divided by 100, plus the abundance of the second isotope times its mass, and if you have more than 2 isotopes, you just keep adding those terms together. Abundance of each isotope times the mass. The sum of the abundances would be 1 or 100% if it's expressed as a percent, and then the isotope masses are the individual masses of each isotope. So in this problem here, what we'll see is that the atomic mass, we're looking for the percent abundance of one of the isotopes. The atomic mass here is given, and we now have 2 unknowns, and we also have 2 other givens. So the mass of each isotope, isotope A being 131, that mass is given. The second isotope has a mass of 133.9767, that's also given to us. So in this problem we have 2 unknowns, which are going to be the abundances of each isotope, and we're trying to find the abundance of the larger isotope, as I've called it B here. All right, so this is going to be our first unknown, this is going to be our second, X and Y as I'll call them. And then if we have 2 unknowns, we need 2 equations. That's what we learned in algebra back whenever we took that. And so with 2 equations, 2 unknowns, the second one is going to be, as I said, the sum of the abundances has to equal 1, okay? So that's going to be the second equation we set up. And we're trying to solve for Y, if we're calling isotope B the 134 isotope, and that means we're going to rearrange this equation to solve for X. X is equal to 1 minus Y, and then we're going to take this and we're going to plug it in for X, okay? So writing all that out numerically then, the atomic mass which is given is 132.2145. That's going to be equal to the first abundance, which we called X, but we're going to call that now 1 minus Y. And we're going to multiply that by the mass of the first isotope, which is 130.9856. Plus the abundance of the second isotope, which we're calling Y, times its mass, which is 133.9767. And then what we said is Y is going to be what we call the abundance of that second isotope, the 134 isotope as we're solving for here. And what we get numerically, I'm not going to go through the algebra, but work it out on your own. I encourage you to do that to make sure you're clear on that. 0.4109, we are looking here for percent abundance. So remember that we have to take, to get it per percent, we have to multiply that by 100. So 0.4109 times 100 will give us that number as a percentage, which comes out to 41.09%. Okay? So in these types of problems, like any of the terms here could potentially be our unknown. So keep in mind that we could have asked you to solve for atomic mass. We'd have to give you the abundances and masses of all those. We could ask you to solve for one of the isotope masses. So there's a few variations in how we set these problems up, but they're all going to revolve around this one idea, this one equation here. All right, do we have any questions on that? All right, so far I don't see any questions coming in on this, so let's go ahead then and move on. to number 7. All right, so number 7 asks for how many moles of sodium ions are present in 65.65 grams of sodium phosphate. Enter your answer with 3 decimal places and no units. So now we're getting into the part of the course that deals with moles, and there's going to be several questions on this exam where the concept of moles and conversions involving moles are going to be fairly important, okay? So what we have in this problem is sodium phosphate. And so what we need to do is first figure out what the formula of that compound is. So this is also a bit of a review. So if we go to the periodic table, this is going to help us for this problem. Okay, so in the periodic table, we see that sodium is in group 1A. So that means sodium is going to have a +1 charge as an ion. And it's going to be paired with phosphate, which is a 3- anion. So we still need to know names and formulas of ions. So we have sodium plus, and we have phosphate 3-, PO4 3-. And again, to find the formula, we need to have equal positive, equal negative charges. The sort of no-brain way of doing that is by just crossing the charges and making them subscripts. And so what we end up with is a formula of Na3PO4. Now that's going to be important for 2 reasons in this problem. One is that we're looking for how many moles of sodium ions there are. So we do need to know the chemical formula to know how much sodium is in that one formula unit. And then also we need to know the molar mass of this to be able to convert mass into moles, as we have to do in this problem. All right, so that's going to be the 2 steps. So the first thing we need is the molar mass, or what's often abbreviated as MW for molecular weight. And so as a review, the way that we calculate molar mass is we're going to add up the individual atomic masses. So again, we need the periodic table for that. So our atomic mass is going to be, we have 3 sodiums, 1 phosphorus, and 4 oxygens. And if we go to the periodic table, we have to find the individual atomic masses of all of those. So sodium here has an atomic mass of 22.99. Oxygen is 16.00. And then phosphorus, which is the other one in this, is going to be 30.97. Typically 2 decimal places is more than enough for these. So if we go back and do the molar mass calculation, we have 3 sodiums that each have an atomic mass of 22.99. If you'll forgive me, I'll leave out units for now just to make things a little bit faster. So that's the contribution from sodium. We have 1 phosphorus in the formula that has an atomic mass of 30.97. If you do this as long as I have, you won't even have to look up these atomic masses anymore, but I don't recommend that lifestyle, but it's you might get to that point eventually. And then we have 4 oxygens with an atomic mass of 16 each. And so when we add all of those together, we get an atomic mass for this compound of 163.94. And remember that we express the units for, a molar mass of 163.94. And we express the units as either AMU or the more useful one, and in most problems, are going to be grams per mole. That means 1 mole of this substance has a mass of 163.94 grams. And now we're ready to do the calculation. So it's always helpful to start with what are we looking for? We're looking for moles of sodium ions. So write out what it is the problem is asking you for. And then our starting point is we have 65.65 grams of the compound, Na3PO4. The first step we're going to do is we're in mass. We want to convert to moles, so we're going to use the molar mass. And so 1 mole of this compound has a mass of 163.94 grams. So that's going to go in the denominator to make sure that the gram units cancels out, divides out. My high school physics teacher hated the word cancel because it's not really a mathematical operation. But anyway, I'm okay with it. And we're going to divide out the units of grams. That gets us into moles of this. Now, a lot of people would make the mistake of stopping here, but remember that this number here is moles of the compound. We're looking for moles of sodium ions that are in that compound. And so what we have to do is we go to the chemical formula, Na3PO4, that tells us that we're going to have 3 moles of sodium ions, because of the subscript of 3 here, for every 1 mole of compound. All right, so it's important when you're calculating moles to know, what exactly am I looking for here. And so we want to do this last step here to figure out how many moles of sodium ions are actually in this. And then what we get numerically is 1.201 moles of sodium plus. And in Blackboard, as we always say, you're going to enter this with no units and typically 3 decimal places or whatever we specify in the problem. All right, so that's sort of the first problem dealing with moles. mass to mole calculations are going to be something that we have to come up with a lot on this exam. So, are there any questions on that? All right, so I think we're all caught up. I want to make sure that it's actually showing. Here we go back. All right, we have another question coming in. So let me go back to the meeting. All right, so the question that just came in was, can you go back to number 6 and go over why we multiplied 4 to 133? It's not 4, it's y. It's my bad handwriting, I'm sorry. So that's our y is our unknown in that problem. Do my y's really look like 4s? Kind of. Sorry. Okay, so this is our unknown x and y as we call them. So it's going to be y. Okay. So while you guys are focused on learning chemistry, I'm going to be focused on learning writing, which I still haven't learned. But that's a y, not a 4, so I apologize for that. All right, so that's our unknown. So we have to do some algebra then here with this equation to actually figure out what that number is. So I didn't go through the algebra, but that's just going to be what your y is when you solve for it using these numbers that I gave up there. Okay, do we have any other questions on this? No worries, no need to apologize. I'm well aware that my handwriting is awful, and anytime you can call me out for it, I do appreciate that, because I'm sure other people will appreciate it as well. All right, so don't worry about that. And we're all set, I think, on the last problem as well. So, and if you do fall a little bit behind, you can always ask questions about previous problems. That's no problem. Okay, on to number 8. So we're going to do more sort of mole conversion problems. So in this question here, we have a compound called catechol, which is 65.4% carbon, 5.49% hydrogen, and 29.1% oxygen by mass. We learned about mass percent a long time ago at the very beginning of this course, but what we're able to do now is we're going to use the mass percent, as this question asks us to do, to find the empirical formula for this compound. So in problems like this, there's a few different setups, but if we're given the mass percents or just the masses directly, we're going to just use those numbers as our starting point. So if you're given mass percents, you're going to assume that we have 100 grams of the compound. And then what that means then is that these percentages tell you how many grams of each element are in 100 grams of compound. That's the definition of a mass percent. And so then we can use the percentages as mass amounts for that 100 grams of compound. So what we're going to do is, if we want to find the empirical formula is going to be the smallest whole number ratio of moles of each element. So we have to take the masses of each element and convert it into moles first. Okay, so for each one we're going to do that. The moles of carbon, we have a mass percent of 65.4, so we're going to have 65.4 grams of carbon in the compound, and we're going to use each atomic mass to convert into moles. I'm not going to go to the periodic table to look those up, but the atomic mass of each of those elements will be on the periodic table to look up for us. And so 1 mole of carbon has a mass of 12.01 grams. So by dividing by that, we're going to convert grams into moles. And so what we get is 5.45 grams of carbon. And then what we're going to get is for hydrogen, we're going to do the same thing. The mass percent for hydrogen is 5.49, so it's going to be 5.49 grams of hydrogen. And then we're going to use its atomic mass, which is 1.008. And so we get 5.44 grams of hydrogen. And then finally, the last one here is going to be the moles of oxygen. The mass percent of oxygen is 29.1, so there's 21.9 grams of oxygen in this 100 grams of compound. And the atomic mass for oxygen is exactly 16 or 15.999, so close enough. And we get 1.82 moles of oxygen. Okay, so then once we have all of the mole amounts, why did I write those as grams? I'm losing myself here. Moles, my bad. So those are moles of each element, and now what we can do is we can write those as the empirical formula. So carbon, there's 5.45, hydrogen, there's 5.44, and oxygen, there's 1.82. Now obviously chemical formulas and empirical formulas are going to be written as whole number ratios, so then what we need to do is divide each of these by the smallest one to make it into a simpler ratio. Okay? And when we do that, when we divide all these by 1.82, which is the smallest number we had for oxygen, what we get is C3H3O. I guess you won't get exactly 3 for hydrogen, but it'll be like 2.999 or something, so close enough. So we get C3H3O, that's the ratio of those three, so that's going to be the empirical formula. All right, so that would be choice A here. One thing that didn't come up on this problem, but could come up in some ones, is that sometimes you'll do this step here where you divide the mole amounts by the smallest one, and you'll still end up with something that's not a whole number. So if we instead got in C1.5, H1.5, O, we'd have to multiply this whole thing by 2 to get rid of the decimal. That wasn't required because we got whole numbers directly, but if you get fractional or decimal numbers, you don't want to make sure you don't want to round too much. You just want to make sure you can get rid of those by multiplying by a small factor. So that can come up at times. It didn't come up here, so I'm going to erase that and not cause any confusion when you look back through the notes, but just be aware that you don't always get whole numbers directly, but you want to just basically convert it to the smallest whole number ratio by multiplying by a relatively small factor that gets rid of the decimal. All right, do we have any questions on that problem there? All right, so that's a pretty typical one. The next one that I'm going to do is a little bit of an extra or bonus question. I don't know if you consider it a bonus to do one more problem, but we did have this question, a request from a student, and it actually is a good one to cover because it's a little bit different variation on that same type of question. So the question that was asked by this student was, again, another compound that contains carbon, hydrogen, and oxygen, also asking for empirical formula, but this time we did combustion analysis. And so what we're giving you instead of the masses of the individual elements is the mass of CO2 and water. So in a problem like this, what you have to do is, first of all, keep in mind, what does it mean to do combustion analysis? So in combustion analysis, you're going to take the compound, which has some formula, CXHYOZ, is a compound in this case of carbon, hydrogen, and oxygen. You're going to burn that in the presence of excess O2, oxygen gas, and you're going to get carbon dioxide and water. Where all of the carbon in the compound ends up in CO2, all of the hydrogen in the compound ends up in H2O. Now, you don't necessarily need to write out this general equation for these types of problems, but this is just to remind you of what's happening. We're burning a compound and we're forming carbon dioxide and water. We're measuring the mass of each of those products, and then we're going to figure out from there the mass of each element that's in this compound. Okay, so what we can do is, for carbon and hydrogen, we're going to use these mass amounts directly. So we're going to find the mass in moles of carbon. We'll do grams and moles. Now remember that we don't necessarily need the grams of each element, but we actually need it in this problem because to get the grams of oxygen, we have to do that by difference. So we know how much compound we burned, and then once we have the masses of carbon and hydrogen, we're going to subtract those from this to get the mass of oxygen. So it's a little bit of an extra step that we need to do, but we're going to have to find both the grams and the moles for carbon and hydrogen to be able to solve this problem. So to get the grams of carbon, actually let's do moles first. You can do it in either order, but it's one less step to do moles. So let's do moles of carbon first. We have 1.471 grams of CO2. And I didn't work this problem out beforehand, so I'm going to wing it, and you guys can see if I can still do this or not. Do I still got it? So we're going to convert that to moles of CO2. We have to calculate the molar mass of CO2, which isn't given, which is 44.02. So that's how many moles of CO2 we have, and then we know that in CO2 there's 1 carbon and 2 oxygens. So how many moles of CO2? That's the same as the number of moles of carbon, because the formula of CO2 is CO2, just 1 carbon in the formula, so equal numbers of moles of those. And so what we end up with is 1.471, sorry. I didn't work this out beforehand, as I said. So we get 0.0, sorry, too many zeros, 0.3342, I'll keep enough sig figs, moles of carbon, and then the grams of carbon is going to be just that number times the atomic mass of carbon. which is 0.401. 3. Okay, so that gives us moles and grams of carbon. Moles first, and then once we have the moles, we just multiply that by the atomic mass of the element to get grams. We're going to do the same thing for hydrogen, but for hydrogen we're going to use the mass of water to figure it out. So we can find the moles of hydrogen first. We have 0.225 grams of water. We're going to use the molar mass of water to figure out moles of H2O. So the molar mass of water is 18.02. And then the only difference here is that H2O, we have 2 hydrogens in the formula, H2O, so there's going to be 2 moles of hydrogen for every 1 mole of water. So make sure we remember that step here. And so what we get for moles of hydrogen is 0. Did I do that right? The number sounds a little bit weird. Let me make sure I didn't mess up my calculation. All right, I was right. So you guys see I'm not perfect. I thought I was wrong once. 0.2497 moles of hydrogen, and then the grams of hydrogen are that number. It's basically an atomic mass of 1. So we don't have to, it's not going to change much. So that's 1.008 grams of hydrogen per mole. That's the atomic mass of hydrogen. Multiplying by that gives us the grams of hydrogen. So we get 0.025172 grams of hydrogen. And then finally, to get the grams of oxygen, this is what we have to do by difference. So to get the grams of oxygen, we burned 0.6943 grams of compound. That's how much compound we burned. We found out that there's 0.4013 grams of carbon in there. And we also found out that there's 0.025172 grams of hydrogen. It's just 17, that's too many sig figs. And so if we do by difference, we can figure out what's the mass of oxygen that's in that compound. And we get 0.2, gosh, I'm not writing well today, 2678 grams of oxygen. And then finally we have to get moles of oxygen as well. So it's going to be 0.2678 grams of oxygen. 1 mole of oxygen has a mass of 16.00 grams, as we've used earlier. And so when we divide that number by 16, we get 0.0167 moles of oxygen. And then finally, the last step is to take these into an empirical formula. So we're going to have C 0.03342. That's the moles of carbon we have. H was 0.02497. And then oxygen was 0.01674. So we're going to divide all of those by the smallest number, which is the one for oxygen. And I'm desperately out of room here. So we're going to divide all of those by 0.01674. And so what we end up with, I believe, is C2. Let me check that that's right. So when we divide the 0.03342 by that, we should get 2. Yeah, we get 1.996, which is close enough to 2. For hydrogen, what we get is hydrogen, we get 1.49, which is close enough to 1.5. and then oxygen we get 1. Okay, so that's what we get when we divide all of the mole amounts for carbon, hydrogen, oxygen by the smallest one, which is 0.01674, the moles of oxygen we have. And then this is a situation where we have to get rid of the fraction or the decimal by multiplying by a small whole number. So if it's something 0.5, you want to double all of those subscripts, and we get C4H3O2. That would be the empirical formula for terephthalic acid. All right, so hopefully I didn't make any mistakes there because I was kind of winging that one, but that would be another variation on the empirical formula problems, which is using combustion analysis to figure out the amounts of each element. So do we have any questions that came up on this? Will this extra question show up on the test? So it could show up on the test. Remember that each problem on the test comes from a bank of questions that's normally, sort of like it's going to be usually about 20 or so different problems that it can choose from. And so when you're dealing with empirical formulas, there's two main variations, and you could see either of those. You could either see the first one we did, which just uses either the masses of the elements or the mass percents directly, or you could have a combustion analysis problem. Both of those problem types are in the question bank, and then you can possibly have them on your exam. You won't necessarily have it, but it certainly could be there. Okay, do we have any other questions? Oh, sorry, we had one come in I just missed. When you were solving for oxygen, where did 0.4013 come from? Okay, so what we're doing for oxygen is we're going to find the mass of oxygen by difference. So 0.6943 is going to be the mass of the compound that we burned. That's given to us in the problem. And then we're going to subtract the masses of the two other elements, carbon and hydrogen. The sum of the masses of the elements is equal to the mass of the compounds. And so 0.4013 is the mass of carbon. We're going to subtract that. 0.02517 is the mass of hydrogen, and we subtract both of those numbers to get how much of that compound is actually oxygen. Okay, anything else? All right, let's get on then with the rest of this. All right, so here we're moving into balancing chemical equations. And so in this problem here, we have barium phosphate reacts with sulfuric acid to form barium sulfate and phosphoric acid. What is the coefficient of sulfuric acid when the equation is balanced with the smallest possible whole number coefficients? So when we're dealing with balancing equations, remember the key is that we have to have the same number of each type of atom on both sides of the arrow, on the left side, which is the reactant side, and the right side, which is the product side. In this problem, we also have to make sure that we get the correct formulas for reactants and products to be able to do that. So barium phosphate is our first one here, and I probably should have told you that barium has the symbol Ba, because it's not one of the first 36 elements. So that you wouldn't have to know off the top of your head that barium is Ba, because it's too heavy, I believe. Barium is down here, but the important part is that it's a 2+ cation. So if you need that on the test, we'll make sure that we tell you that barium has the symbol Ba, because it's not one of the first 36 elements that you're expected to know. But the point is that barium is going to be 2+, and then phosphate, as we saw earlier, is PO4 3-. So that's the first reactant. We have to make sure we get the formula correct for that. So that's going to be Ba3 and then PO4 2 if we cross the charges and make them the subscripts. All right, so the first formula, the first reactant is barium phosphate, Ba3 PO4 2. The second one is sulfuric acid. Sulfuric acid is going to be the acid of sulfate, which is SO4 2-. Since it has a 2- charge, it's going to have 2 H+ to balance that out. And so it's going to be H2SO4 is the other reactant. And then let me leave a little bit of space so I can put coefficients in later. And then the products of this are going to be barium sulfate. So on the product side, we have barium, which is, as we said, a 2+ cation paired with sulfate, which is SO4 2-. So the formula for barium sulfate is just going to be one of each, BaSO4 plus 2-2, so the charges balance out with one of each. And then the other product is phosphoric acid. Phosphoric acid is the acid of phosphate, PO4 3-, which means it needs to have 3 hydrogens to balance that 3- charge. So H3PO4 is going to be the other product. So these are reactants and products, and now we have to balance it and figure out the coefficient for sulfuric acid. And when we do this, in this problem, it's helpful. We have a lot of polyatomic ions, phosphate and sulfate. So instead of necessarily thinking about individual atoms, it's helpful to think about individual ions that are in the problem. And so what we'll see here is that we have 2 phosphates in barium phosphate. And so that means we need to have 2 phosphoric acids as a product. And then similarly, we have 3 bariums in the first reactant, which means we have to have 3 of these as a product. And then if we put a coefficient of 3 in front of that, that gives us 3 sulfates, which means we also need to have 3 H2SO4. So for reactions like this that involve ionic compounds, acids, and bases, typically the coefficients are relatively small. You'll get large coefficients if you're balancing a combustion reaction, for example. But for these types, you're going to have relatively small coefficients. And the coefficient for sulfuric acid is this one here, which is 3. So the correct answer for this is 3. So we could give you, a number of different types of chemical equations to balance. But again, the key point is to make sure that you have the same number of each atom on the left and on the right. And if we check that, we have 3 bariums and 3 bariums. We have 6 hydrogens, 6 hydrogens. And then for the other ions that don't separate, the polyatomic ions, 2 phosphates, 2 phosphates, 3 sulfates, 3 sulfates. So everything matches up there. So any questions on balancing equations? There will likely be a question on the test where we ask you to do that just by itself. But again, balancing equations is also something that's going to be a part of a lot of other types of problems that we have. And so it's going to be, something that we have to think about throughout this part of the course. Okay, so any questions on this one? All right, so what we're moving into now as we get through the next few questions is going to be stoichiometry. And so the first question here is if we have 3.25 grams of butane burned in the presence of excess O2 to form carbon dioxide and water, what is the mass of CO2 that forms in grams? Okay, so this is a typical mass-to-mass stoichiometry problem. We're giving you the mass of one of the reactants, and we're asking you to find the mass of one of the products. So the first thing we need is a balanced equation. So this gives us a little bit of practice with that again. Butane is C4H10, as we're told. The other reactant in a combustion reaction is oxygen O2. And then we're always going to form in a combustion reaction, as we talked about earlier, carbon dioxide and water. Okay? So those are going to be the reactants and products for this one. And then to balance it out, what we're going to have is we have 4 carbons in the reactant, so we need to form 4 CO2s as products. We have 10 hydrogens as part of this also, so we're going to have 5 waters to make sure we have 10 H's on both sides. And then we're going to balance oxygen last. So in this problem here, we have 4 times 2 is 8 plus 5. We have 13 oxygens on the right. And so then on the left, we also need 13 oxygens. It's O2. So the way we get 13 is by taking the 2 and multiplying it by 13 over 2. So that would give us a fractional coefficient. We could use this form of the equation. There's nothing wrong with having fractional coefficients. If we asked you to actually balance this in a problem, we actually would probably want it to be whole numbers. And so to get it into whole numbers, we just have to, again, multiply by a factor that gets rid of the fraction, in this case 2. So with whole number coefficients, it would be 2 C4H10 plus 13 O2s goes to 8 CO2 and 10 water. But it's important to note that we can use either form of this equation to approach the rest of the problem. You don't necessarily have to balance it with whole numbers unless we ask you to do it specifically for that problem. So now we can go ahead and get into the stoichiometry part. And we have, in this case, we're only told the mass of one reactant, which is butane. And we don't have we're telling you that O2 is in excess. So because we only have the mass of one reactant, and because we're telling you that the other one's in excess, both of those things tell us that we don't have to worry about eliminating reactant in this problem. We can go ahead and just start it directly. So what we're looking for is the mass of CO2 that forms, given that we're burning 3.25 grams of C4H10. And now from here, we can go through and do the conversions that we need. So when in doubt, as I always say, convert to moles first. We have grams of this. We're going to convert it to moles first. We're going to use the given molar mass. So 1 mole of C4H10 has a mass of 58.14 grams. And then from there, we can start using mole ratios to convert moles of this reactant C4H10 into the moles of CO2, which is the product we're looking for. So we can use either form of the equation. I'll use the bottom one, which is whole numbers, and we see that we have 8 moles of CO2 for every 2 moles of C4H10. So those numbers are just the coefficients from the balanced equation, which tell us the ratio of how many moles of CO2 we form for however many moles of C4H10 we combust. So the 8 comes from the coefficient for CO2, the 2 is the coefficient for butane, and we write it in this way because we want moles of C4H10 to cancel out. We want to convert into moles of CO2. This question is asking for grams of CO2, so the last step is then to use the molar mass of CO2, which I probably should have given you in this problem, but we used it earlier, 44.02 grams of CO2 per mole. And then what we come up with in this is going to be 9.84 grams of CO2. This one specified 2 decimal places, and so we'll leave it at that and enter that number into Blackboard. All right, so this is a typical mass-to-mass stoichiometry problem where you're starting with mass of one substance, converting it into mass of another using these types of mole conversions. The key step for stoichiometry is this step here, using coefficients as mole ratios to convert between one substance and another. All right, so any questions on that problem there? I think I missed a couple of questions earlier, so let's go back in time a little bit. So we had a question about why is H plus with the coefficient of 3 for phosphoric acid is because PO4 is 3 minus charge. So we thank you for answering that amongst yourselves. I appreciate that. And then the question here that just came in about this last problem is why did you use the 8 and 2 coefficients? So we could have used either form of the equation. So I used 8 and 2, which is the whole number coefficients that I balanced down here. But you could have also used 4 and 1 if you would have just stuck with the first equation. It's the same ratio, 8 over 2 or 4 over 1. And the 8 and the 2, as we said, come directly from the balanced coefficients. So what the coefficients mean is that for every 2 moles of C4H10 we react, we form 8 moles of CO2. So we can use that as a ratio to convert between the amounts of the two substances. 8 moles of CO2 are going to form for every 2 moles of C4H10. Or alternatively, we could have done it as 4 over 1 if we had balanced the equation in the first way. When you're doing stoichiometry, it doesn't matter how you balance the equation as long as it is balanced. Whether it's whole numbers, fractions, whatever floats your boat will be fine, but it does need to be balanced for that to work. Okay? All right, and then another question that came in was, will combustion analysis ever require us to find the limiting reactant first? The answer is no, because for combustion analysis, you're burning the whole compound and it's always in the presence of excess O2. Now for stoichiometry problems, as we're going to get to here in a second, it will be sometimes necessary to figure out what the limiting reactant is, but for combustion analysis, that's never really a consideration you have to worry about. Okay, anything else? Great. Let's go on then. Plugging along, we're running a little bit behind, but thank you for bearing with my technical problems, and we're going to move faster now, I think. All right, so here we have another stoichiometry problem. We have the theoretical yield of gold 3 chloride in the reaction shown below if 29.6 grams of gold are combined with 10.9 grams of HOCl, which is called, what is that called? Hypochlorous acid. That's the active ingredient in bleach, as it turns out. So we want to know what's the theoretical yield of gold chloride, and then we have excess HCl. So in this problem, we're told that the HCl is in excess, but we're giving you masses of 2 of the reactants. Gold, which is 29.6 grams, and HOCl, which is 10.9 grams, okay? And so anytime we have amounts of 2 reactants, whether it's in grams, moles, volume of a solution in a molarity, like whatever the amount that's given is, if we have amounts for 2 reactants, we have to be able to figure out the limiting reactant first. So that's sort of the dead giveaway, that we're going to have to first figure out what the limiting reactant is to be able to solve this problem. And the way that we do this is there's a few ways we do it, but the way that I like to do it myself is to find the moles of each reactant and then go through and find what I call the stoichiometric ratio. So what we do is find the moles of each reactant first. So for gold, we have 29.6 grams. The atomic mass of gold, which we didn't give you, but that's on the periodic table, is going to be 196.97. So 1 mole of gold has a mass of 196.97 grams. It's one of the heavier naturally occurring substances, naturally occurring elements. And so that gives us moles of gold, which is 0.150 moles. And then to find what we call the stoichiometric ratio, this is going to be important for determining what the limiting reactant is. We take that number for gold, the number of moles that we got is 0.150, and we divide it by the coefficient in the balanced equation. The equation here was given to us with coefficients already written. It has a coefficient of 2, so we're going to divide that number by 2 and find that the stoichiometric ratio for gold is 0.075. Okay, we're going to do the same thing for the other reactant where we know the amount, which is HOCl. So the moles of hypochlorous acid, HOCl, is going to be 10.9 grams. The molar mass of HOCl was given to us here is 54.46. Is that right, though? Did I screw that up? Hang on a second. I might have messed up the molar mass of that. So give me a hot minute. Yeah, I gave you the wrong molar mass there. I'm really sorry about that. That should be 52.46. I thought that number sounded wrong. So I apologize for that. If you would have used the wrong molar mass, you would have still gotten the right answer, I think. So like, don't worry about it too much. And so we get 1 mole of HOCl is 52.46 grams. I gave you the wrong mass in the problem, so again, my bad. And so what we get for moles of HOCl is somewhere around 0.208. And then the stoichiometric ratio for that is going to be that number divided by its coefficient, which is also 3. No, not also 3, is 3. Which is 0.0693. Okay? And the one that has the smaller stoichiometric ratio is going to be the one that's our limiting reactant. And so what we see is 0.0693 is smaller than 0.075, so that identifies HOCl as our limiting reactant. And so now we're ready to go ahead and do the calculation we need to do, and we're going to start now with the moles of our limiting reactant HOCl. Okay, so what we're looking for here is the theoretical yield of AuCl3, the grams of AuCl3 that can form. We probably should have specified that it's in grams, but that's what we're going to do. So the grams of AuCl3 that's going to be forming, we're going to start with moles of limiting reactant, 0.208 moles. Once we figure out what the limiting reactant is, we don't want to use the stoichiometric ratio numbers anymore. That just tells us what limiting reactant is. Okay? So we have that many moles of our limiting reactant. And then since we're already in moles, we can use the coefficients now directly. So we're going to have 2 moles of this product forming, coefficient of 2 for AuCl3, for every 3 moles of HOCl. And then finally, we want to find the mass of AuCl3, even though I didn't necessarily clearly indicate that in this problem. The molar mass is 303.32. And so what we get when we do those conversions is 42.1 grams. And I think we wanted 2 decimal places, so I guess I should follow my own directions and call it 42.06 grams of AuCl3. All right, so that would be the number we'd enter in. So for a limiting reactant problem, the last step is the same. It's just stoichiometry again, but we have to first figure out what the limiting reactant is, and then any calculations we do in that problem have to start with limiting reactant, because that's going to determine how many moles of each product or how many grams of each product forms, okay? So a couple of issues with this problem which were my fault. We should say theoretical yield in grams and I had the wrong molar mass for that other reactant, but we can still work out the steps and figure out what we're doing. So any questions on this one? All right, I'll come back and check again later if you have anything that comes up, but let's get on with the show. All right, so now we're dealing with, we're already in sort of more of chapter 6 material, starting now with conductivity of solutions and other reactions that happen in solutions. So the first one is, which of the following aqueous solutions would not conduct electricity at all? So if we're talking about electrical conductivity of a solution, we're dealing with what are called the electrolyte properties. So as a quick review of that, a strong electrolyte is going to conduct electricity. And there are basically two types of substances that would be classified as a strong electrolyte. Either a soluble ionic compound, so when we dissolve an ionic compound in water, it produces a strong electrolyte solution, or if you have a strong acid dissolved in water, that would also give you a strong electrolyte solution. And then if you have a weak electrolyte solution, these conduct electricity but not as well. So basically, in these types of solutions, you're going to form some ions. So the key is, for an electrolyte solution, you need to have ions in solution. So the strong electrolyte, your soluble ionic compound dissociates into ions, your strong acid dissociates into ions. In a weak electrolyte, some of the molecules you dissolve dissociate into ions, but not all of them do, so you don't get as many ions in solution, and thus you don't get as much electrical conductivity. So these would be weak acids or bases, are really the only classes of substance that fall into the weak electrolyte category. Both of these types of solutions, I'm terrible at drawing the braces, so let me just draw a square bracket. Both of these types of solutions conduct electricity, okay? So whether it's a strong electrolyte or a weak electrolyte, the solution will conduct electricity. Strong electrolytes conduct electricity better typically because they have more ions, but they both have electrical conductivity. And then the ones that don't conduct electricity are called non-electrolyte solutions. And these are going to be when you dissolve a covalent compound in water, in one that's not an acid or a base in particular. They don't break up into ions, and so you don't have any ions in the solution, you don't conduct electricity. All right, so there's some acids and bases, or most acids and bases are technically covalent compounds. But if you have a covalent compound that's not an acid or a base, these ones do not conduct electricity at all. So basically, in this problem here, we're looking for which solution would not conduct electricity at all. You need to find the one that is a non-electrolyte. So if we go to choice A, nitric acid, HNO3, is a strong acid, which means it would make a strong electrolyte solution. So that's not what we're looking for. Calcium chloride, CaCl2, this is an ionic compound. It's soluble, so when you dissolve that, you're going to get a strong electrolyte solution. So that's not the correct answer either. The next one, though, CH3CH2OH, this is clearly a covalent compound because it's all nonmetals in the formula. And if it ends with an OH, we call that an alcohol, and those are going to give you non-electrolyte solutions. So this is going to be a covalent non-electrolyte solution, and so this would be likely our answer choice. Let's check the other ones as well. KOH is another soluble ionic compound, so it's going to form a strong electrolyte solution and conduct electricity, so that's not what we're looking for. H3PO4 is an acid. All acids are electrolytes. This one is a weak acid, as it turns out, so it would be a weak electrolyte solution, but still one that would conduct electricity to some extent. So the only one that doesn't conduct electricity is CH3CH2OH. Now, before I move on, I want you to be aware of one thing about problems like this is that there's two similar types of compounds that we could ask you about. So ones that have, that end in OH, so like this one here, CH3CH2OH, or anything, carbon or hydrogen with an OH at the end, those are going to be called alcohols, and those are going to be non-electrolytes. So that's sort of the classic non-electrolyte solution. Dissolve an alcohol in water. Sugar would be another one, but alcohols are very common. However, if the formula ends with OOH, for example, acetic acid, which is CH3COOH, if it has this group at the end, this is a weak acid. They're called more specifically carboxylic acids. You don't need to know that. But there's just a small difference there that you need to be aware of, which is that if it just has OH at the end, it's an alcohol and it's a non-electrolyte. If it has OOH at the end, like acetic acid does, it's going to be a weak acid and then a weak electrolyte. So make sure you're able to keep those straight when you're distinguishing electrolyte properties in particular. All right, any questions on that topic? All right. So now we're getting into relationships involving moles in solution. So we have a solution of 25.65 grams of calcium perchlorate, and we want to know what is the concentration of perchlorate ions in molarity, capital M. So the first thing we need for this problem is we're going to need the chemical formula, because what we're looking for here is the molarity of perchlorate, which is going to be defined as the moles of perchlorate ions per liters of solution. So remember that molarity is moles per liter. And so we need those two quantities. We're given the liters of solution directly, so that's going to be given to us already. But we need to find moles of perchlorate to be able to do this. And we then need to know the formula of the compound, because we need to know how many perchlorate ions are in this compound. So we have calcium perchlorate. As you'll recall, calcium is in the second column of the periodic table, so calcium forms 2+ ions. And then perchlorate is a polyatomic ion with the formula ClO4- with a 1- charge. So the correct formula for this compound, if we again cross the charges and make them subscripts, is going to be CaClO4 taken twice. So there's 2 perchlorate ions in one formula unit of this compound. That's going to be key for figuring out the number of moles. So now we have to figure out how many moles of perchlorate there are, and it's just going to be a series of mole conversions, very similar to one we did earlier on in this practice test. So we're looking for moles of perchlorate. We have 25.65 grams of the compound. We're in grams. To get to moles, we're going to use the given molar mass. So 1 mole of this compound has a mass of 238.98. So that gives us moles, but we don't want to stop here because we're not looking for just the molarity of the compound, we're looking for the molarity of perchlorate ions. And so we have to use this last conversion here. So the formula is Ca with 2 ClO4- anions. So there's going to be 2 moles of ClO4- that are going to dissolve for every 1 mole of the compound. And so when we work that out, we get 0.2147 moles of perchlorate ClO4-. And then putting this into the equation, we have 0.2147 moles. And then the liters of solution is given directly as 1.23. And then dividing those two gives us a molarity of 0.175 molar. Just entering the number in the blackboard will give us 0.175. All right, so that's just a problem dealing with the definition of molarity. That's something that will certainly come up on most of your exams. And it's just, again, moles of solute per liters of solution. Just pay close attention to which solute, whether it's the whole compound or the ion that we're asking you about. Okay, do we have any questions on this one? Okay, so then the question here that came in about the previous one is, why is the OH and KOH not alcohol, and what makes the compound a soluble ionic instead? So KOH is an ionic compound because it has a metal in the formula. So remember that if we have a metal with a non-metal, those are going to be called ionic compounds. So it's a K+ ion with an OH- anion, and those are going to be typically soluble ionic compounds, and they're going to be strong bases when they're dissolved in solution. The ones that just end in OH would have all non-metals in the formula. So these are going to be all non-metals, usually just carbon, hydrogen, and then an OH at the end. So the difference between C and D is that this one has all non-metals, so it's a covalent compound. This one has a metal and non-metals, so that makes it an ionic compound, and then thus is going to be classified as a strong electrolyte. Okay? Any questions? And it's soluble because it has potassium in the formula, which, as we'll talk about in a little bit, makes it soluble. All right, anything else on the most recent questions? All right, so let's get on with the next one here, which is going to be another type of molarity question. So we have 125 milliliters of water, and we're adding it to 225 milliliters of 0.254 molar NaCl, sodium chloride. What is the final concentration of NaCl? Assume volumes are additive and enter your answer with 3 decimal places, blah, blah, blah. Okay, so this is what we should recognize immediately as a dilution problem, because we just have one substance, we're not reacting with anything, and we're taking an aqueous solution and we're adding pure water to it. So remember that when we add pure water to a solution, we lower the concentration, we lower the molarity, and that's referred to as dilution. So whenever you see dilution, you should immediately think of M1V1 equals M2V2, and that's the equation we're going to use. So what we're looking for here is, it doesn't really matter what we define as M1 and V1 and M2 and V2, but we have basically a solution that has 225 milliliters and 0.254 molar. So that's going to be, I'll call that M1 and V1. Typically the ones that we have the molarity and the volume of, I call M1 and V1, but you don't have to do that. It's up to you. And then what we're looking for as our unknown is M2, the final concentration. Now for V2 though, this is where you have to be a little bit careful in this problem. V2 is not the amount of water that we're adding. V2 is going to be the total volume of the solution after dilution. So our V2 is going to be, we're telling you here that we're adding 125 milliliters to the initial solution, so it's going to be the volume we started with, 225 milliliters, which is V1, plus the amount that we're adding, 125 milliliters. All right. We're telling you here to assume additive volumes, which means that the final volume is going to be the sum of what we started with plus the water that we added. So 350 milliliters. All right, so that's going to be our V2. We want to make sure we use the right number for that. And then what we're going to solve for is the only unknown that's left, which is M2. So the final molarity is going to be M1V1 divided by V2. And because we have a ratio of V1 over V2, we can use whatever volume units we want, in milliliters, liters, whatever else is your fancy. And so we're going to just put the numbers in directly without converting them. The initial molarity is 0.254. That's given to us. The initial volume is 225 milliliters. And the final volume after we add the water is 350 milliliters. So milliliters divide out, and then we're going to get an answer that should be a smaller molarity. We're always decreasing the molarity when we dilute, and it comes out to 0.163. Okay? So dilution is another topic that we saw in chapter 6. One relatively simple equation, M1V1 equals M2V2. Questions? Okay, it's gone. The next question here now deals with everybody's favorite topic, which is solubility rules. And so we're asking which of the following mixtures will not form a precipitate. So there are going to be questions that deal with solubility rules where either you have to just consider the solubility of an individual ionic compound, or you have to think about mixtures of compounds like we do here and decide which one will produce a precipitate. All right, so the first thing we have to do for these problems is we have to figure out what are going to be the two products that form when we mix these solutions together, and then decide if one or both of those is a precipitate. So we're looking for one that will not form a precipitate. So basically we want to find which one has both products being soluble. To do this, there's some helpful things to remember. So in these types of problems, we're only going to ask you to distinguish soluble from insoluble. We're not going to ask you which one is more soluble or less soluble or anything like that. It's just sort of a binary process, soluble, insoluble. So that's important to keep in mind also, even though it's not important for this particular problem, but it never will be. It's always going to be just soluble versus insoluble. All right, so in the first mixture here, KCl plus AgNO3, remember that what we do is when we mix two solutions together, we're going to swap the cations and the anions. So the cation from the first reactant is going to pair up with the anion from the second, and vice versa. The anion from the first reactant is going to pair up with the cation from the second. So with KCl and AgNO3, we're going to get potassium paired with nitrate to make KNO3, and we're going to make silver chloride, Ag, paired with Cl, AgCl, both +1, -1 cations and anions in this case. Now we want to know if either of these is insoluble, and so we remember that anything that has a group 1A cation, lithium, sodium, potassium, rubidium, cesium, All of those are soluble. Anything with nitrate in it is also soluble. So KNO3 is definitely soluble. But silver is one of the cations that's almost always going to be insoluble unless it has a nitrate anion. So now when we do this reaction, Ag is paired with Cl, Ag, silver chloride. That's going to be insoluble. So that one forms a precipitate. That's not going to be our correct answer. For answer choice B, we have ammonium sulfate and lead perchlorate. And so we're going to form ammonium paired with perchlorate. So it's going to be NH4COO4. NH4 plus 1. Perchlorate is minus 1. And then the other product is going to be lead 2 plus paired with sulfate, PbSO4. And lead is a lot like silver in that when you have a lead 2 compound, it's almost always insoluble unless nitrate or perchlorate is the counterion. And so there you go, that's going to be insoluble as well. So both A and B will form a precipitate, so they're not the correct answer. In choice C, the two products are going to be sodium paired with chlorine, so it's going to give us NaCl as one product. And then the second product is going to be barium 2 plus paired with carbonate, CO3 2 minus, BaCO3. And carbonate is one of the anions that's always going to be insoluble unless it's paired with lithium, sodium, potassium, all those group 1 cations, or if it's paired with ammonium. So carbonates are usually insoluble. This would be an example of that. So that's going to form a precipitate. Choice D, the two products that we form are going to be NaOH NaOH is going to react with FeCl3. We're going to form sodium with chloride again, so it's going to form once again NaCl, which is definitely soluble because it has a sodium cation in it. The other product here is going to be iron 3 with hydroxide, so it's going to form iron with 3 hydroxides, FeOH3. Transition metal hydroxides are insoluble. So hydroxides are also usually insoluble except for the group 1A cations and except for some of the group 2 cations. But any transition metal hydroxide you would assume is insoluble, so that's going to precipitate. And then finally, the last one here, these two is going to form calcium with chloride, so it's going to be CaCl2, calcium 2 plus, Cl1 minus. And then the other product is going to be ammonium NH4 plus with nitrate, NH4Cl. And what you'll notice is that this is definitely soluble. Anything with the ammonium cation, NH4 plus, is soluble. And then calcium chloride, most chloride salts are soluble. The only insoluble chlorides would be like silver, lead, and copper 1, not as common, and then the mercury, so these last two aren't very common anyway, but these two are the big two, silver and lead chloride. So calcium chloride is soluble. Most chloride compounds are. So both of these products are soluble, which means that there would be no precipitate formed here, and that leaves choice E as our answer. Okay, do we have a question? Oh no. All right, I briefly cut out of the meeting, but I think I'm back. So then we had a couple questions related to this. So F minus is always soluble except with silver and lead 2. We didn't deal specifically with the F minus solubility. I think it's a little bit different than the rest of the halides, but I don't think we'll ask you any questions about fluoride in particular. I think it's generally similar to chloride. So if you had silver and lead fluoride, they would be insoluble, and most other fluorides are. There's a few more exceptions with fluoride, and we don't expect you to know those though. And then the question is, wait, why did NH4 not pair with NO3? Let's see if I made a mistake or which one you're talking about. It should, you're right. So I made a mistake there. So that should just be ammonium nitrate. But it doesn't change the conclusion because ammonium is always soluble, nitrate's always soluble. So this product would always be soluble. Thank you for pointing that out. Any other questions? All right, so let's move on to the next ones. Number 16, what are the spectator ions when solutions of barium nitrate and sodium phosphate are mixed together? So recall that spectator ions are ones that remain soluble both on the reactant side and the product side. In other words, they don't form a precipitate, they don't change their form at all. They're just dissolved aqueous ions on both sides of the equation. All right, so we have to write the equation out here. So it's barium 2 plus, as this problem gives you the hint of in the answer choices, and with nitrate. So the first reactant is going to be BaNO3 2 The reactants are always aqueous, they're always soluble in these types of problems. So it's going to be barium nitrate. Then the other one is sodium phosphate. Sodium is Na+, phosphate is PO4 3-, and so we're going to get Na3PO4. And then the products are going to be, again, this is just an ion exchange reaction. We're going to swap the cations and the anions. So we're going to get barium paired with phosphate. I won't go through the details of that, but the formula for that compound is going to be Ba3PO4 And then the other product is going to be sodium paired with nitrate, which is just NaNO3. So this first form of the equation here is going to be called the molecular or formula equation. And we can put some coefficients in to balance it, and then also recognize that we can identify what is soluble and insoluble right away. So if we look at this, we have to make sure that everything's balanced. So we have 3 bariums on the right, so we need to also have 3 on the left. So we're going to put a coefficient of 3 there. We have 3 sodiums on the left. We want to have 3 on the right, so we're going to put. Sorry, that's not going to quite do it for us though. So we have 2 phosphates here, so we have to have a 2 there to make 2 phosphates. Now we have 6 sodiums and then 6 sodium nitrates. So to make sure everything's balanced, these are the coefficients. And so that's going to be the balanced equation. And then if we can figure out which ones are soluble and insoluble, sodium nitrate definitely soluble because it has sodium and nitrate. Both of those, the cation and the anion, are always soluble. But barium phosphate is a lot like carbonate, where most phosphates are insoluble except for sodium, potassium, lithium, and so on, the group 1 cations. So this one will be our solid. It's going to form as a precipitate. All right, so that's going to be the complete equation. To figure out spectator ions, what's helpful to do is to separate these into the ionic equation, right? The total ionic equation. So everything that's written as AQ, aqueous, we're going to divide up into the individual cations and anions, representing that they're dissolved in solution in that form. So for the first reactant here, we have barium nitrate is going to separate into 3 barium 2 pluses. And then we have 3 times 2, which is 6 nitrates. The second reactant, we have 2 times 3, which is 6 Na+. So the reactants are always going to be aqueous, and if they're ionic compounds, they're always going to separate into their ions. And then we have phosphate, which is, we have 2 of those, 2PO4 3-. So those are the ions that are going to be on the left side. On the right side of the arrow, though, barium phosphate forms a precipitate, so that's not going to be separated into ions on the product side. That's just going to be Ba3PO4. But then the other product, which is sodium nitrate, is going to be still separated because it's dissolved as aqueous. So it's going to be 6 Na+ and 6 NO3-. Okay, so that's the total ionic equation. And then to identify spectator ions, we have to find the ions that appear as aqueous ions on both sides. And so what we'll see is we have 6 nitrates on the left, 6 nitrates on the right, 6 sodiums on the left, 6 sodiums on the right. So that means Na+ and NO3-, sodium and nitrate, are going to be the spectator ions, choice B. This question didn't specifically ask for it, but if we were asked for the net ionic equation in this, what we would do then is then eliminate the spectator ions. The ones that appear on both sides of the arrow, you can think of them as sort of canceling out. And so the net ionic equation would just be 3 barium 2 plus 2 phosphates goes to barium 3 PO4 barium phosphate. So in a precipitation reaction, then that ionic equation is typically just going to be the 2 ions that combine to make the precipitate. Make sure you have the correct number on both sides. Okay, so are there any questions on precipitation reactions or net ionic equations? All right, so the question is it necessary to balance the equation to get the spectator ions? Not really, but sometimes what we will ask in these types of questions is, which species appears in the net ionic equation or the total ionic equation, and for those types of questions, we will also have a coefficient associated with it. So you'll want to make sure that you choose the answer choice that is the correct ion, the correct reaction or product, as well as the correct coefficient. If we're just asking you like we did here, what is the spectator ion, you don't really need to do that. That's not necessarily going to be the case, okay? So there are differences in the types of questions we can ask. Sometimes it matters what the coefficient is, sometimes not. In this question, though, you are correct. We probably didn't have to think about coefficients. We just have to identify which species are soluble and insoluble to figure out which one's going to end up being the spectator ions. Any other questions? All right, 17. Now we're on to acid-base chemistry. So this is a topic that we did not cover live. This was after spring break, after we were abruptly converted to an online class. So we're going to go through this one here, which is a sort of what we call a titration problem. Now, titration problems often invoke fear in students for some reason. They hear the word titration and they want to crawl under the rug. But titration is really not that bad. It's just solution stoichiometry. So it's stoichiometry, but very often we're using molarity and volumes as our units instead of grams and moles. So it really is just stoichiometry, and it does involve moles. And often what you're going to do in problems like these sort of titration type problems where you're neutralizing an acid with a base or vice versa, what you're typically doing is you're going to be finding moles of one of the substances, either moles of the acid or moles of the base, and then you're going to do something with that quantity depending on what the question is asking. All right, so in this question we have 2.34 grams of an unknown diprotic acid with 2 acidic protons. So that means the general formula for this unknown is going to be H2X, 2 hydrogens in the formula plus some anion that is paired with. And it's neutralized with 0.375 molar NaOH solution. So this is an acid-base reaction, which we talked about before, but the stoichiometry aspects we didn't really cover in the live portion of the course. If it takes 40.9 milliliters of the sodium hydroxide solution to neutralize the acid, what is the molar mass of the unknown acid? So as I said in these types of problems, if you're doing acid-base neutralization, titration type problems, very often you're going to be asked to find the moles of the acid or the moles of the base, whichever one you don't know, and you're going to do something with that. So if we're looking for an unknown molar mass, remember the definition of molar mass is grams per mole. So if we want to find the molar mass of H2X, we need to know what mass of H2X we used, which is given. So that one's given to us. Then we need to find out how many moles of that substance we have. So anytime we want to find an unknown molar mass, we want to find these two quantities, grams and moles. Dividing the two gives you the molar mass, grams per mole. Okay? So we already have the mass of the unknown that we used in this experiment, in this titration, 2.34 grams. But we have to find the moles using the titration data. So to be able to do that, we have to figure out what is the balanced equation for the reaction of H2X, which is an acid, with NaOH, which is a base. For these types of problems, it's not particularly important that you get the products right. You don't really care what the products are in these, because we're figuring out mole ratios of reactants, but we can write them out to be complete and make sure we understand that part. So when you're reacting an acid and a base, you're always going to form water, and then you're going to form an ionic compound that includes the cation that was paired with hydroxide and the anion that was part of the acid. So we will get Na2X, because X is a 2- anion in this case if it's a diprotic acid. Okay? So those are reactants from products. The important part is that we balance the left side. So our acid has 2 acidic hydrogens, which means it's going to need 2 OH minuses to react with it. So we're going to put a coefficient of 2 there. That also then results in the formation of 2 moles of water as a product. But again, we don't really care about the right side of the equation. We just need to make sure that we know that the acid and the base react in a 1-to-2 ratio. That's going to be key for any stoichiometry problem, is knowing, any titration problem, is knowing the ratio that the acid and the base react in. So now we're ready to figure out how many moles of H2X were in that sample. And so what we're going to do is we're going to start with the NaOH solution, because for that we know the molarity and the volume. So if we have the volume of NaOH, which is 40.9 milliliters of NaOH solution, and then we want to use its molarity to figure out how many moles we have. So the difference with solution stoichiometry is that instead of going from grams to moles, we're usually going to go from volume of solution to moles by using the molarity as a conversion factor. So 0.375 molar means that we have 0.375 moles of sodium hydroxide in every 1 liter of solution or every 1,000 milliliters. So we could do this in 2 steps. We could do moles per liter and then or convert this to liters and then do moles per liter. But I usually like to combine these and take a little bit of a shortcut. And that recognizes that molarity, which is moles per liter, can also be written as moles per 1,000 milliliters because 1 liter and 1,000 milliliters are the same thing. So that allows us to convert into moles of NaOH. And now we can use the coefficients in the balanced equation to figure out how many moles of H2X that were involved with that. Okay, so we have a coefficient of 1 in front of H2X, or no coefficient, which implies a coefficient of 1. And that's going to be per 2 moles of NaOH because it has a coefficient of 2. And so what we end up with is 0.00767 moles of H2X. And that's going to be the number that we put back in here to calculate the molar mass. So the grams is 2.34. The moles that we just found is 0.00767. And then dividing those with 1 decimal place, 305.1 grams per mole is the correct number. Okay? So in a titration problem, you're going to use the information we give you to find moles of one of the substances, and then from there it's a question of what you do with that quantity. So do we have any questions on that problem? Something we didn't cover until the class was already converted to online, but there is going to be one problem on the test that does involve titrations. All right, moving on. Now that I'm gasping for air. All right, the last 3 problems. So just a little bit of background and history. The person who put a lot of these exams together in the past, which we have since modified and refined every year, but they're sort of based on a question bank that's been around for a while. The person who originally put these together really loved redox equations, oxidation reduction reactions, which was the last topic in chapter 6, which again we did not cover before spring break, was only in the videos that I posted after. And so there's going to be 3 questions on this exam that deal with oxidation numbers and then redox reactions. So 1 question dealing with just the concept of redox, and then the last 2 questions are going to be balancing redox equations. So just be prepared for that. It's not the easiest, not the hardest topic we've covered. It's not a lot of math or anything. It's just learning sort of the approach to follow and some of the little tricks of the trade that come up the more examples that you do. So definitely do a lot of example problems on these because you want to get used to sort of the rules for oxidation numbers as well as the approach that we use to balance redox equations. Okay, so number 18, in which of the following is the correct oxidation number for nitrogen given? And so for these, we have to go through and remember the rules for oxidation numbers. So in choice A, we have nitric acid HNO3. So in typical covalent compounds, oxygen is going to have an oxidation number of -2. So there's some elements, hydrogen and oxygen in particular, that pretty much always have the same oxidation number with rare exceptions. So oxygen in most covalent compounds is -2 unless it's oxygen bonded to itself. And then hydrogen is going to be +1. Okay? And so if we have 3 -2s and a +1, the sum of the oxidation numbers has to equal 0 because this is a neutral molecule. The sum of the oxidation numbers equals the charge. So 3 -2s is -6. We have +1, and that means nitrogen has to be +5 so that all of those add to 0. So nitrogen's oxidation number in HNO3 is +5, so that's incorrect. One thing to keep in mind about oxidation numbers is that the largest oxidation number you can have is the group number. Nitrogen is in group 5 on the periodic table, so +5 is as large as it could possibly be. All right, so choice B, NO2, once again, oxygen is going to be -2 in just about every covalent compound with rare exception, except for O2 or H2O2. And so if it's -2, that's 2 -2s is -4. That means nitrogen has to be +4 so that they add up to 0. And so this one should be +4. It's given as +2, so that's wrong also. In choice C here, NCl3, chlorine can have a few different oxidation numbers, but it's usually -1 if it's bonded to something that's less electronegative. So nitrogen is less electronegative than chlorine, or they're very similar. But usually if chlorine is the outer atom in this, like NCl3, you're going to call this -1 And then if there's 3 minus 1s, nitrogen has to be plus 3. And so 3 minus 1s and then plus 3, so that's going to be also wrong. That should not be minus 3. And then finally the last one, D, N2, for any neutral element, whether it's just the atom by itself, as you often see for metals, like Na for sodium, Fe for iron, Au for gold, if it's just a neutral element by itself, or if it's a diatomic or polyatomic, like you often see in the non-metals like N2O2, F2, Cl2, P4, S8. But if it's just an element with only one type of atom in the formula and there's no charge involved, then the oxidation number is 0. And that's the only time the oxidation number is 0, is for those neutral elements. All right, so this one says minus 1. That's wrong. So the correct answer for this is none of the above. None of these have the correct oxidation number for nitrogen. Okay, so that's how we assign oxidation numbers. There's going to be one problem that could very well just ask you to do that. The last two problems that we'll get to here in a second are going to be balancing redox equations, where we need to use the oxidation number as part of that. So any questions on oxidation numbers before I move on to the last two, which is balancing redox equations? All right, so let's get to these. They're both very similar types of problems, but some differences between them. So in this problem here, in the types of problems you're going to have on the exam, typically what we're going to do is just ask you to supply the coefficients. You're not going to have to predict reactants and products for redox equations. You're not going to have to add anything to the reactants or products side. We're going to give you all the reactions and products. You just have to find the coefficients. It's just a balancing exercise. But we're going to, in many of these cases, we want to use a specific approach for doing that, which I covered in the lecture that would have been for this past Monday. And you definitely want to review that if you haven't seen that yet, if you're still having a little bit of trouble with it. So let's go through this one here. We have H plus permanganate, MnO4 minus, plus NO forms manganese 2 plus, and NO2 and water. Okay, so the first thing to do is write out the reactants and products, which are going to be given to you. Then what you have to be able to do is find the oxidation numbers for every atom in the equation. And so that's why it's good that you want to get fast and efficient at assigning oxidation numbers. So the ones that are easy are going to be the ions by themselves. So if it's just a monoatomic ion, a single atom of charge, the oxidation number is the charge. So H plus has an oxidation number of plus 1. Mn2 plus on the product side has an oxidation number of 2 plus. So if it's just a single ion by itself, the oxidation number is very easy. For the rest of these, it's going to be a little bit of work to get them. And so for MnO4 minus, we have 4 oxygens, which are going to be minus 2. The overall charge in this case is negative 1, so what we want is the oxidation numbers to add up not to be 0, but to add up to negative 1. The oxidation numbers always add up to the charge, okay? So we have a negative 1, we have 4 negative 2s, and so then algebraically that means manganese must be plus 7. So we have a plus 7 oxidation number on manganese, and then 4 minus 2s add up to give you minus 1. All right, so that's going to be the oxidation number for manganese there. And then in NO, it's going to be relatively simple. We have a minus 2 for oxygen, which leaves plus 2 for nitrogen, so that they add up to 0. NO2, similar story. We actually did that one in the last problem. 2 negative 2s on oxygen, and then that leaves plus 4 for nitrogen. We're assigning the oxidation number of each atom, not the total oxidation numbers for all of them. So oxygen is just minus 2 for each of them. And then water, which is going to show up in almost every redox equation, so you should get very familiar with this. Negative 2 for oxygen, plus 1 for hydrogen. All right, so those are the oxidation numbers. Then what we want to do is find the ones that are changing. So we notice that manganese goes from plus 7 to plus 2. So those are changing. We're going to draw a bracket between those. And then nitrogen is going from plus 2 to plus 4. So the first thing we want to balance in a redox equation are to make sure that we have the same number of electrons being transferred between what's being oxidized and what's being reduced. And to get the number of electrons, what you're going to do is you're going to look at the difference, the change in the oxidation number. Now, technically, one species is going to gain electrons, one species is going to lose electrons. For these types of balancing problems, we don't really care about whether they're being gained or lost. We just need to know the number of them. And so manganese is going from plus 7 to plus 2. That's a difference of 5 electrons because the oxidation number is changing by 5. And then nitrogen is going from plus 2 to plus 4. That's a difference of 2 electrons because the oxidation number is changing by 2. And so then what we want to do is we want to find the smallest the least common multiple of these to make the number of electrons equal. So we have 5 and 2. We want to make these equal to each other. So what we can do is we can double this to make it 10 electrons, and then multiply that by 5 to make it 10 electrons. So then to do that, we have to add coefficients. So if we have coefficients of 2 in front of each of the manganese species, that's going to be a total of 10 electrons. And then if we add a coefficient of 5 in front of NO and NO2, those are each changing by 2 electrons, and so if we have 5 of them, that's going to be a total of 10 electrons, which is now going to balance out the number of electrons that we have for what's being oxidized and what's being reduced. All right, so that's going to be the coefficients on those. Once we set those, we don't want to change them. So this 2 and this 5 and this 2 and this 5, don't touch them anymore. The rest we have to balance are going to be H plus and water, and we're going to do that by inspection. Typically, you're going to do water first by making sure that oxygen is balanced. So what we'll see is on the left side of the equation, we have 2 times 4 is 8, plus 5 is 13 oxygens on the left. On the right, we have 5 times 2 is 10, so we need 3 more oxygens to make sure that there's 13 on each side. So we're going to put 3 in front of H2O. If we added 3 waters, that gives us a total of 6 hydrogen, and so we need a 6 in front of H+. So that's going to be how we balance this one, and then this one is looking for the sum of all the coefficients. So the sum is going to be 6 plus 2 plus 5 plus 2 plus 5 plus 3, which comes out to 23, choice A. All right. And so don't forget, if there's any coefficients that are not there, that means it's a coefficient of 1. All of these had coefficients greater than 1, but don't forget about those that don't have a coefficient. That would count as a coefficient of 1. Okay, so that's how we balance redox equations. It's a lot of steps, and like I said, a lot of practice is going to be helpful for you to learn how to do this. So, any questions on redox equations? So the question was, how many oxygens were there? There should be, I think, 13 on each side if I counted them right. So if we go back to the problem, there's 2 times 4 from permanganate is 8. Plus 5 from NO, that's a total of 13. And then on the right side, we have 5 times 2 is 10, plus 3 is also 13. So the last step was to figure out that we needed 3 more on the right side, because we had the 13 on the left from these 2 species. We have 10 from NO2, that means we needed 3 more, so that's why water got a coefficient of 3. So when you're balancing the last pieces, it's going to be what we call by inspection, where you just have to make sure that the number of atoms on each side is correct. Usually it's going to be oxygen and hydrogen that you're balancing last very often in these problems. Okay? Any other questions on this one or this topic? All right, so to close this off, we'll get one more just similar to that. This one I think is maybe a little bit more complicated, but not too much worse, hopefully. Okay, so we have this reaction here. Again, it's just another one where we give you the reactants and products. We want the coefficient, and this time we want the sum of the coefficients on the reactant side. So make sure you read the problem closely to figure out what it's asking, but the main work for you is going to be to just balance the equation. Okay, so we're going to go through and do this. And first we need to assign the oxidation numbers. Go ahead and do it up here with what's already written on the exam. All right, so what we have here is, the first one is chromium chloride, which is an ionic compound. In ionic compounds, the oxidation number is just the charge of the ion. So chloride is always -1. It's group 7 of the periodic table, so it forms a -1 anion. And then if we have 2 -1s, that means the chromium is going to be +2. This is a transition metal, so it could have a few different possible charges. In this case, it's +2. The second one is nitric acid. We did that one earlier. -2 for oxygen, +1 for hydrogen, leaves a +5 for nitrogen. And then on the product side, we have nitrate, NO3-. If we're just removing an H+ from it to make the ion NO3-, we don't change any of the oxidation numbers. So NO3- is still +5 for nitrogen, -2 for oxygen. If we just do acid-base chemistry, we don't change the oxidation numbers of whatever's left. But then chromium here, because we have 3 NO3-, that oxidation number changes to +3. And then the other ones, we have HNO2, so it's going to be -2 for oxygen and +1 for hydrogen. 2 -2s is -4, +1 is -3. We need a +3 on nitrogen for those to add up to 0. And then we have our old friend water, which is -2 and +1. And then HCl, which is -1 and +1. So hydrogen is always +1 if it's in a covalent compound. and then chloride is usually -1, as is the case here. So those are the oxidation numbers. Again, make sure you're fast and efficient at doing this. And now we can start identifying the ones that are changing. So what we have here is chromium is going from +2 to +3, so that's one of the ones that's changing. And then nitrogen is going from +5 to +3. But there's a little bit of a difference here, which is that nitrogen is going from +5 to +3, but also there's going to be some nitrogen that's staying at +5. So we're actually going to have to balance HNO3 in two parts. So there's a couple ways of handling that, but let's write out the reactants and products here at the bottom again. And what you have to keep in mind is that HNO3 is going to get balanced in one sense by the number of electrons that are transferred, but there's also going to be additional nitrogen, additional nitrate in particular, where the oxidation number is not changing, so we're going to have to add additional HNO3s to make sure that the total number of nitrogens on each side is the same. So in some cases, you have to sort of play sort of both games, balancing by redox numbers and balancing by inspection sort of simultaneously. All right, so I wrote out these again so we can put the coefficients in a little more easily. So let's count the number of electrons that are transferred. Chromium goes from +2 to +3, that's a 1 electron change. Nitrogen goes from +5 to +3, that's a 2 electron change. And so we want these to be equal. All we have to do is double the number of electrons for the chromium, which means that each of those gets a coefficient of 2. So the ones that are changed by 1 electron, we're going to give a coefficient of 2 to make sure that there's a total of 2 electrons. And then for HNO3, it's going from +5 to +3. That's a 2 electron change. So what we want is a coefficient of 1 there initially, and a coefficient of 1 there as well. However, we're not quite done with HNO3 because in addition to the 1 HNO3 that's getting reduced at HNO2, there's an additional 6 here. There's 6 nitrates, 2 chromium nitrates, so 2 with 3 each, total of 6 nitrates additionally that aren't changing their oxidation number. So we have to change this coefficient of 1 into a coefficient of 7. Another way of doing this is balancing this in two parts where we have HNO3 twice. There's a couple ways of handling that, but we have to have a total of 7 HNO3s. One of them being reduced to HNO2, the other 6 are going to be forming the nitrate counterions that are present in chromium nitrate. Now from there we can do the rest by inspection. So if we want to do oxygen first, we see that on the left side we have 21 oxygens. On the right side we don't want to change any of the coefficients except for the last two now. We have, that's 9 times 2 is 18, plus 2 is 20 oxygens on the right. So we have 18 from chromium nitrate, 2 more from nitrous acid. So we have 1 more that we need. So this is going to get a coefficient of 1 also. And then for HCl, we need to make sure that the chlorides are balanced. So on the left side, we have 4 chlorines. That means we need to have 4 HCl's on the right because that's the only 2 places that chlorine appear. So those are going to be the coefficients on both sides. And then the sum on the reactant side, which we're asking for here, is going to be 2 plus 7, which is 9. And it might be possible that you have to just enter in this number on some of the questions as well. All right, so we finally made it. A little bit slower because of some of the technical hurdles at the beginning, but I think we sort of figured out that this works reasonably well. And I thank you all for your patience and for all your questions. We're going to ask another couple. I'll take some more questions if there's any left. So we do have one here. Can you explain how you got +5 in chromium nitrate? So I kind of went fast on that, but basically one thing that's helpful to know is that if you're just doing acid-base chemistry, if you're just adding or removing H+, you don't change the oxidation numbers. So here we're going from HNO3 to the nitrate anion, the NO3-, where all we're doing is removing H+. So that's not going to change it. Now there is a faster way to do this. So not faster, maybe more, not faster, but more rigorous way of doing this. So in ionic compounds, it's usually helpful to think of the ions separately and do the oxidation numbers of each ion individually. So in chromium nitrate, we have chromium 3+ and then NO3 -1. So because the charge on the metal is 3+, that's going to be its oxidation number. Anytime you have an ionic compound, the charge is the oxidation number. For NO3-, what you have is the oxygens are still going to be -2. They're still bonded to another nonmetal. You have 3 -2s. The sum has to equal -1 because it's a -1 charge ion, and that leaves +5 for nitrogen. So +5, 3 -2s. The sum is -1, which is the charge of the nitrate anion. So that's how you would go about that a little bit more deliberately. Okay? No need to apologize for questions. Glad that was answered. And then we have that the hydrogen is not balanced. Is that true? Let's see. What did I do wrong here? I think yeah, I think there's 7 on each side. So you have 1 from HNO2, 2 from water, 4 from chlorine. That's 7, and then 7 from HNO3. So it's in 3 pieces on the product side. Each of these last 3 all has hydrogen in it. But I think there's the same number on both sides. Okay, so no worries about that. Glad I could clarify. And anything else on this question, this topic, this whole review before I let you off? And I will put the video online a little bit later. It's going to take me a while to convert it to the right format and get it on YouTube, but it will be there by this late afternoon or early evening. And then you'll have a chance to review this over the weekend. As far as my availability for questions next week, my schedule is pretty flexible now that I'm stuck at home all day, every day. So I welcome you to send questions by email if you prefer that. If you want to set up a video chat, or phone call, or whatever works best for you to get questions answered in person, that's certainly possible as well. And then I have the regular office hours that are going to be 2:45 to 3:45 Monday and Wednesday. But like I said, my schedule is very flexible, so I'm certainly willing to set up appointments any other time. There's one last question about the webcam on the exam, everybody's favorite topic to discuss these days. So if our webcam doesn't work, how do we know that the exam settings have changed so we do not need to do the webcam verification step? So that's going to be all set up in Blackboard. It won't be obvious until you actually go in to take the exam. But when you take the exam, you're going to have a version of the exam that's in your exam folder, and you're just going to click on that one version of the exam that's going to be in Blackboard. So you're not going to have, there's not going to be any confusion about which exam you take. Just click on the exam. It should be set up for you properly. If it's not, obviously let us know, but we think we have everything set up to do that automatically. The other question is, what happens if you don't have a scientific calculator? I'll have to check I don't think we're relaxing the rules on scientific calculators, so try to get your hands on one if you can. There is a calculator built into the Lockdown browser. It's not the most powerful or best one to use, but it does work for most of the simple stuff we have to do here, like just adding and subtracting and multiplying and dividing. So you can use the calculator that's built into Lockdown browser. Hopefully you can get a scientific calculator, because I think we're still going to make that a requirement that the only calculators we allow are scientific. But if there's any other questions about that, we can discuss it later on, no problem. But I think we're going to require scientific calculators or using the one that's built in. Okay, any other questions? All right, you're all very welcome for doing this. Certainly appreciate being able to connect with you virtually. I'm glad you had so many good questions to keep the discussion going. And again, I wish you the best on preparing for this exam, for everything else in your life right now. And please stay in touch. I know we're going remote, but I do want to make sure that I'm still available for you and that we learn as much as we can. So, thank you all for participating, and have a great weekend. Mm-hmm.